friction is one of those invisible forces that quietly shapes almost every part of our daily lives. We rarely think about it, yet without friction, walking would be impossible, cars couldn't stop, and heavy machines would fail to grip the ground they work on. In this episode, we'll explore the physics of friction and see how it powers everything from safe roadways to massive earth-moving equipment. At its core, friction is the resistance to motion that occurs when two surfaces interact. It comes in two main forms: static friction, which prevents objects from sliding until a threshold force is reached, and kinetic friction, which acts once the object is already moving. The size of this force depends on the coefficient of friction, a simple number that reflects how grippy a pair of surfaces are. For example, rubber on asphalt has a much higher coefficient than steel on ice. Rolling friction adds another layer, showing how wheels and ball bearings reduce energy losses compared to sliding. On the road, friction is what keeps us safe. Tire treads are carefully engineered to maximize grip under different conditions, whether it's a sunny highway or a wet monsoon road. Without friction, brakes would be useless, because the wheels would never be able to transfer force to the ground. This is why technologies like ABS, the anti-lock braking system, were invented. They allow drivers to maintain steering control even when braking hard, by keeping friction in the sweet spot between gripping and sliding. The physics of friction explains everything from why cars skid on rain-slick roads to why racing tires are completely smooth, optimized for maximum grip on dry tracks. But friction isn't just about cars and roads. It's at the heart of heavy machinery, especially earth-moving equipment like bulldozers, excavators, and loaders. These machines depend on controlled friction to push, dig, and lift massive amounts of earth. Instead of wheels, bulldozers use caterpillar tracks, which spread the machine's weight over a large surface area. This not only prevents sinking into soft soil but also increases grip, giving the machine the friction it needs to move forward with power. Excavators rely on hydraulic systems, where seals and pistons must balance friction carefully. Too much, and efficiency is lost; too little, and the system leaks or fails. In muddy or icy conditions, operators are constantly fighting against low-friction environments that reduce control and stability. Engineers must carefully balance friction. Too much friction leads to wear, wasted fuel, and overheating. Too little friction results in slipping, instability, or even catastrophic failure. The challenge lies in designing systems that harness just the right amount. Lubricants, coatings, and advanced materials all help control this balance. In roadways, engineers add rough textures or grooves to improve traction, while in machines, they reduce unnecessary friction at moving joints to improve efficiency. Innovation continues to reshape how we use friction. Modern tire technology now uses nanomaterials and computer-designed tread patterns to deliver grip and efficiency across multiple conditions. Earth-moving equipment increasingly relies on advanced composites and smart designs that can adapt to terrain. Engineers even use powerful simulations to predict how friction will behave in complex real-world situations before a single machine is built. In the end, friction is not just resistance, it's a tool. From the roads we drive on to the machines that build our cities, friction is the hidden partner that keeps our world moving. It challenges us, it wears down our machines, but with smart engineering, it becomes an ally, one that makes stability, safety, and progress possible. This video is part of the series Physics for Engineers: Foundations that Build the Future, an initiative of the Physical Sciences Consultorium. If you enjoyed this episode, don't forget to subscribe, explore more of our content, and stay tuned as we uncover how physics shapes the world of engineering.